Hi, I'm Paul. We are doing Leetcode, must know, interview questions. Today's challenge is word search. This is a medium rated challenge. We did a previous one called word search. Actually, where was that? No, word search 2. Wait a minute, is this word search 2? Oh, there's word search 2. Okay, hold on. Yeah, what category was this in? Word search 2. Okay. So that was putting the words in a tree because we were looking for multiple words. So we put the words in a tree and then searched the tree. And word search, I actually looked at that word search 2 to see if maybe we could reuse some of the code from that. And it doesn't really work that way. I mean, it's a different problem. In this one, for example, we're only looking for one word. So, putting it in putting words in a tree doesn't really help. There was another thing that made it a little bit, another thing that made it a little bit different, and that is this right here in the constraints. Okay, so we have board length, M and N. The board will be either somewhere between 1 by 1 and 6 by 6. Length of the word that we're looking for will be somewhere between 1 and 15. Board and word, they can consist of both lowercase and uppercase letters. And in the other one, we used the the ability, like if all the letters are uppercase or all the letters are lowercase, then you can subtract a character, an A, lowercase or uppercase, from letters. You can get an index from 0 to 26, and you can keep track of letters that way. But in this case, lowercase, uppercase, it doesn't really make sense. It's better to just go straight through it and compare the result to the word, letter by letter. We can build up the word. We can do a depth first search, build the word up letter by letter, and just compare the current letter to the letter at the current index of the word. And there's a follow-up here. Could you use search pruning to make your solution faster? And I'm thinking, if you do a depth first search, what do they list for topics here? Backtracking. Well, yeah, backtracking. Okay, so we're using depth first search with backtracking, but I think it prunes automatically. That is, we are going to go through the word matrix row by row. There's a number of different ways of pruning this. For example, if we look at example 1, the word we're looking for is A, B, C, C, E, D. Maybe I should say string, because that's not really a word, is it? But if we start at the top left, the A matches, and let's say the algorithm it's going to look in all 4 directions if possible: up, down, left, right. Let's say it looks to the right next, and it says a B. All right, we've got that. We're going to look to the right. C, right, that's good. We're going to look to the right. E, that's not what we're looking for. So we backtrack. We prune that search. We don't keep going and generate every possible 6-letter combination from every square. So that gets pruned right away. All right. Now let's say we go down. We go down. That's good. Down, right. That's no good. Prune it. Down. E, it's good. Go to the right. Prune it. Go to the left. We're done. In this case, we're not going to deal with a lot of the letters at all. So let's say we start here and we're looking for S-E-E. So we look at this and say, no, it's no good. We throw it out. B, throw it out. C, throw it out. E, throw it out. So it seems like a depth first search backtracking algorithm is self-pruning. I mean, unless I'm misunderstanding what they mean by that. So let's try an implementation. Okay, so there are some variables that make sense here as class variables. And then we don't have to pass them around. We're going to have a second method here. We're going to have a depth first search method. So some of these things we can use as class variables. So one would be the height and width of the board. The letters that they're using are M and N. Let me refresh my memory on which is which. Okay, so M is actually the height, N is the width, but we'll use M and N. So private int M, private int N, private string word, that'll be the input word that we're looking for, and private it'll be characters. They're coming in as characters, right? Yeah. Private char, it's a matrix, and yeah, what we can call it board. That's what they're calling it here. All right, so then the first thing that we do in the exist method is to initialize those variables. So we can say m equals board dot length. And this is given as part of the problem definition. M equals board dot length. N equals board with an index dot length. So we'll say m equals board dot length. We'll say n equals board as 0 dot length. We'll say this dot word equals word, and this dot board equals board. All right. The next thing we're going to do is we're going to initiate a depth first search from every square. And again, I guess you could count as pruning the fact that we're going to stop when we find the word. So in example 1 over here, we are going to find the word starting from the first square. So we're not going to do a depth first search at all from 11 of the 12 squares. All right. So let's set up a nested loop for int I equals 0, I is less than m, I plus plus. For int j equals 0, j is less than n, j plus plus. Depth first search. Let me think about this. I was just going to say, well, we could return the result of the depth first search, but that's not right. The depth first search could fail, and then we would move on to the next square in the matrix. So let's say if the depth first search, and we should talk about We should talk about what the depth first search is going to look like. If not O, 0, then return true. If the depth first search returns true, then we will return true. Now, what are we doing with the depth first search? Okay. Depth first search, I, J, and 0. So that represents whether we can successfully search from the IJ position of the grid, from the IJ square, starting from the character at index, well, what are we going to call the index? Let's say we call the index K. So we have IJ and K. In this case, we're going to pass in IJ, and we're going to start by passing in 0. So can we successfully search from the IJ position and starting from character 0 of the word? Okay. Yeah, that's probably enough. We'll go through the rest of it as we write the method. If we iterate through all of the squares and we have not returned true, then we're going to have to return false. Okay. Now, the depth first search, private, Boolean, DFS, int I, int J, int K. All right. So this is going to be recursive. Base cases, if K equals word dot length, minus 1, that means that we are now looking at the last letter of the word. So what we're going to return is whether or not the character at board IJ, equals word dot char at K. If it does, then we'll return true. We found the word. If not, we'll return false and, move on. Okay. Another base case here is if board IJ is not equal to word char at K, return false. What does that mean? It means we passed in I and J. That gives us a square, but if that square does not match the character that we're looking for, which is word char at K, then we have to stop. So we'll return false. Okay. If we get past those, it means that we matched a character. We didn't match the final character, but we matched an intermediate character. All right. There's something that we have to do here. We've done this in some previous exercises, and that is there's a rule here somewhere, right? Yeah, it's right there. The same letter cell cannot be used more than once. So we have to have some way to indicate that we've used the letter in a cell. So we are now at board IJ, and we are going to take and save the character at board IJ and replace it. And it doesn't really matter what we replace it with, as long as it's not a letter. Okay, we replace it with something other than a letter because that will stop the search from looking at that character. What does that mean? Well, it means, for example, if we are going through number 1 here, C, we get to C. I don't know, is that a good example? S, E, yeah, I mean, so let's say we get from here and we get to here to B, we get to C, and then we get to C. Let's say the algorithm is set up so it looks up, down, left, right. The first thing it's going to do is look up. Well, we don't want it to look up at that C. We can't use that because we've already been there. So we mark it, and then the search sees, oh, that's not a letter, I can't use that, and it'll go some other way. So we save it. We save it because if the search fails, we're going to have to replace it. But we need some way to handle directions here. Int directions, we can do a direction array. We'll initialize it to, I'll tell you how this works. -1, 0, 1, 0, -1. All right. We use those in pairs. So where do we go next? All right. One possibility is we'll take the first pair, that's row and column. So subtract 1 from the row and leave the column as it is. That will go up. All right. The next pair. This is not right. The next pair, 0 and 1. What would that do? Leave the row as it is and move and add 1 to the column. So that would move to the right. Take the next 2, 1 and 0. If we add 1 to the column, leave the row alone, that will go down. And the last pair, 0 and -1, leave the row alone, subtract 1 from the column, and that'll go to the left. So using those 4 pairs, we can look at all the adjacent squares. All right, let's do for int. I've used about all the letters here. Let's do like D for direction. Int D equals 0. D is less than 4. This is our index into the directions array. D is less than 4, D plus plus. Okay. And we'll say int. We can use X and Y. I mean, we've used M and N as a row and column. We could even use row and column. Okay, let's do it. Let's use X and Y. Actually, let me think about this for a second. Okay, yeah, I think that'll be fine. We can use x and y. So let's say int x equals I plus dir s d. Okay, uh, and int y equals j plus, it's not a j plus dirs d plus 1. All right, so that gives us the next adjacent square. Now, we have to check and see if that square is in the bounds of the matrix. So, let's do this. I should skip a line. Let's do if x is greater than or equal to 0. That's okay. And x is less than m. That would be okay. And y is greater than or equal to 0. That would be okay. And y is less than n. Okay, that's good. And it's a little bit more here. And board x, y is not equal to a dot. That means we've already visited that square. And, all right, so this is the recursive call. We have, if we get past all that, we have successfully added another letter, and what we're going to do is continue the depth first search from the square x, y, and the index k plus 1. Now, if all that is true, I don't want that there. If all that is true, then we can return true. All right. If we get out of there without returning true, then we're going to have to backtrack. And what that means is we are going to have to replace the letter that we saved. So board ij is going to go back to C, and we are going to return false. So no, we didn't find the word. I think that's it. Let's take one more look at this. All right, so we come in, we initialize the class variables, m and n, which is height and width. The word and the board, we set up a nested loop to iterate over every square in the board if we need to. And if we are able to successfully execute a depth first search starting from the square 0, 0, starting from the first letter of the word, then we're going to return true. If not, we're going to return false. All right, how does the DFS work? When we go into the DFS, first of all, we're going to check and see if we are looking at the last letter of the word. And if we are, and it matches, we can return true. On the other hand, if it doesn't match, we've got to return false. We will also return false if the character that we're looking at in the matrix does not match the character at the appropriate index in the word. All right, what's next? Look at all the adjacent squares. Up, down, left, right. Save the character if we match a character, we will do a recursive search to DFS from the new square, the square where we just found a correct letter. If we can't find the word, then we've got to backtrack. We've got to come back. We've got to put the letter that we saved back in instead of the dot and return false. That said, am I over-explaining this? I see that this is becoming kind of a long video. But anyway, oh, did I click run? I didn't even mean to click it. Let me click it again to make sure that I actually clicked it. Oh, okay, so it is accepted. Let me move this over and submit it. All right. Okay, runtime. I mean, you know, it takes a while. It takes a while to run this. The runtime on something like this is going to be it's going to be exponential. But we are kind of, you know, in the ballpark of where most people ended up. What was I going to say? So that's words. We're searching for one word. It's a depth first search with backtracking. It's all pretty standard. What is the runtime of this? Well, worst case, we've got a nested loop that goes through a matrix. So it's m times n times, and then at each square in the matrix, we've got 4 choices. We can go up, down, left, or right. But we really don't have four choices. We have 3 choices because going back to the square that we came from is not an option. So it's m times n times, let me think, 3 to the length of the word. Do we even keep track of the length of the word? I guess we could call it L, 3 to the L. Let's see what they come up with here. M times N times 4 to the K. Okay, but they're using K as the length of the word. And it's not 4, it's 3. Because we can't, we don't have 3 directions we can go from each square. Worst case, we don't have 4. You know, we have 3 because you can't visit the thing twice. But okay, close enough. Hope you enjoyed the video. Please feel free to like, subscribe, comment, and see you next time.